Okay, welcome to another seminar in the Physics Meets ML series. Today we're glad to have Hidenori Tanaka and Daniel Kunin co-presenting. Hidenori is a senior research scientist at the newly formed NTT Physics and Informatics Lab in Sunnyvale, California, and a visiting scholar at Stanford. He studies problems at the interface of physics, neuroscience, and machine learning. Before joining NTT PHI Lab, he was a Massillon Fellow at Stanford University with Surya Ganguly and Daniel Fisher, and did his PhD at Harvard. Daniel Kunin is a PhD student at the Institute for Computational and Mathematical Engineering at Stanford, advised by Surya Ganguly and Daniel Yamins. His research focuses on computational neuroscience and deep learning theory. And today they'll tell us about neural mechanics, symmetry, and broken conservation laws in deep learning dynamics.
Great. Thank you so much for having us here today. I'm Daniel, and I'll be taking the first half of this presentation, and then Hidenori will be taking the second half and conclusion. So please interrupt us if you have any questions. And yeah, looking forward. So this is joint work as well with Javier Sagaste-Brena, Surya Ganguly, and Daniel Yemens that we just published this past year. Okay, so for some context, as we all know, deep learning has been wildly successful, yet many of its inner workings are still quite mysterious. In particular, if you were given a data set and task, and you wanted to construct a deep learning system for that data set and task, there's a myriad of design choices you would have to consider. For example, the architecture. What architecture are you going to use? What nonlinearities? Will you use batch normalization, residual connections? And then how are you going to train that network on that task? Are you going to use weight decay? And if so, how much? Are you using momentum? What learning rate schedule are you going to use? Batch size? Or maybe you want to use the adaptive gradient strategy. And all of these choices shape the trajectory that network will take during training, and in particular, its final trained state. And currently, many of our design choices are based on more heuristics and trial and error of what works in the past, what didn't. And so, broadly speaking, I think this is the goal of many of us, is that a better understanding of the dynamics of that pink trajectory that network takes will be necessary for a principled exploration of the vast design space. And so the question that our research starts with is kind of broadly a broad question, that is, what, if anything, can we quantitatively understand about the learning dynamics of state-of-the-art deep learning models driven by real-world data sets? Of course, this question is quite difficult because deep learning models have millions of parameters. They're compositional functions composed of linear and nonlinear transformations. And they're trained in a realistic setting with discrete updates on random batches of data. Many of the existing works, broadly speaking, that have made progress in this direction have made major simplifying assumptions on the architecture. For example, early works might consider, well, maybe we can't consider any arbitrary neural network, but if we constrain ourselves to a single hidden layer, in this setting, we can make exact predictions about the dynamics that might inform how the dynamics of the state-of-the-art or the commonly used models are working. Or a different series of works might say, well, actually, we can think of multi-layer networks, but if we constrain ourselves to linear activations, in this setting, it's essentially the network is just doing over-parameterized linear regression, and the network is linear in the input space, but in the parameter space, it actually has nonlinear complex dynamics, but dynamics that we can solve exactly. And then maybe more recently, broadly speaking, there's a set of literature that's taking infinite width limits in the number of neurons, maybe most famously the neural tangent kernel approach, where in this setting, the network is no longer linear in the input, rather it's nonlinear in the input, but linear in the weight space, in the parameter space. And all of these approaches have led to interesting insights on the dynamics of real deep learning models or empirically used. But in this work, we're going to kind of take a different approach. And so rather than trying to introduce simplifying assumptions on the architecture or optimizer, we're going to make our problem easier. We're going to try to identify certain parameter combinations or parameter statistics that we can understand exactly. But that won't give us the full picture lens of what the network is doing. But in this setting, we won't be making any assumptions on the architecture or optimizing. So to make that a little bit more concrete, we're going to consider a VGG16 convolutional neural network. This is a state-of-the-art millions of parameters convolutional neural network used in many visual classification tasks. And if we were to consider each element of these convolutional blocks, their value through training, and we just plot that value on the y-axis and training on the x-axis, and we can see that there's kind of complex dynamics at t=0. That would be how we initialize the neural network with some random Gaussian distribution. We're color coding in this case. Each line in this plot is a parameter, a single value element of one of these convolutional blocks, and the color is which block it belongs to. And we can see that the dynamics move through training in some sort of manner, and yet also at any point it looks quite stochastic and noisy. However, if we combine some of these parameters in a certain way, so in this case what we're doing is we're plotting the Euclidean norm, the squared norm of each filter from this convolutional block. So these convolutional blocks are composed of 32 maybe, or 64, 128 different filters. And if we looked at just the norms of those filters through training, we see much smoother dynamics. And so the goal of this work is going to be trying to understand, can we understand the function underlying those dynamics? And as you'll see, we'll build up a theory that can describe that function exactly. And so that's where we're going with this work. So if there's any questions on just the general setup, this would be a good time. Otherwise, I'll start heading into the specifics of how we're going to build that theory. Okay, great. So we're going to do this. Yep.
So why did you choose the Euclidean square norm specifically?
Yeah, so that's going to be the first step, is actually identifying what are these parameter statistics that we can solve exactly. And so that should make sense in a sec. So on that question, yeah, the first part is actually really about that. So what we're going to do is we're going to identify symmetries in the loss function and demonstrate how these symmetries constrain the gradient in Hessian geometry. In the part two, actually, I guess this is more about that question. And in the second section, we'll show how these symmetries lead to conservation laws of certain parameter combinations. And that will explain that answer under gradient flow dynamics. However, those conservation laws won't be empirically true. And so, and the reason will be that the gradient flow is too simple of a realistic model for real world SGD. And so in part three of this talk, we'll be building up a more realistic continuous model for stochastic gradient descent. And finally, in part four, we'll combine this realistic model with the gradient and Hessian geometries introduced by symmetry to derive simple ODEs that we can solve exactly, and demonstrating kind of the functional form for those dynamics. And then we'll conclude with some concluding remarks. Okay, so part one. So a symmetry is going to be a property of a function, and we'll say a function f of theta possesses a symmetry if it is invariant under the action psi on the parameter vector theta. So this action psi is going to be parameterized by some value alpha. And if f of psi of theta is equal to f of theta for all theta alpha pairs, then this function f, we'll say, has a symmetry. And we'll make that clear in a sec, just with a simple example. In particular, we'll say that we show in our work that if a function possesses a differentiable symmetry, so if psi is differentiable with respect to alpha, then the gradient and the Hessian of the original function f have certain geometric properties that are dependent on the form of that transformation psi. In particular, the one that we'll use a lot in this work is that the gradient f of f at any point in parameter space, so for any value of theta, is always orthogonal to the vector field generating symmetry when you evaluate that vector field at the identity element of the symmetry. And so in this work, the brackets will denote inner products. So gradient of f is a vector in this case, and the delta or the psi is the vector field generating the symmetry, and so that's just the inner product. So let's make this clear first with an example. Consider this really simple example, x squared plus y squared. We have two, so theta in this case is just x and y, the vector x, y. And we can see that indeed this function has a differentiable symmetry. If I rotate for any value of x, y, if I rotate that point around the origin by some rotation alpha, then the value of f of x, y is unchanged. And so in this case, psi is this, I guess it says phi here, but psi is actually this rotational action. In which case, then we would say that that implies that the gradient and the Hessian of this function should have a certain geometry dependent on psi. In particular, if we look at the first property of the gradient, then the gradient of this function is just at the coordinate itself. So the gradient of f at any point xy is just 2 times xy. So the gradient vector field is just radiating out from the origin. The vector field generating the symmetry evaluated at the identity element, in this case that would be 0, alpha equals 0, there's no rotation, is negative yx. And you can see that this vector field is this circular vector field around the origin. And if we were to look at the inner product of these two at any point in parameter space for any value of xy, then indeed at any point these two vectors are orthogonal to each other. And so we can see, and while this might seem okay, that's like very simple, this is actually a really powerful tool for understanding much more complex functions, where maybe taking the derivatives is could be quite hairy or complex or involve lots of chain rule and matrix multiplications. And so now we can say that actually without even having to evaluate the gradient, if we can identify a symmetry in the function, then we know that form of that symmetry, then we have already a very good understanding of the geometry of that gradient and its Hessian. So now let's go back to deep learning. Why is this a really powerful tool for understanding deep learning? Well, in fact, in deep learning architectures, nearly every parameter, in fact, every parameter of the VGG network, for example, is involved in at least one symmetry. So VGG 16 with batch normalization, I think has something like 10,000 different unique symmetries in the network itself. And each of these symmetries will constrain the gradient in some deterministic way that we now understand. So let's talk about these different symmetries. In this work, we'll talk about 3 different symmetries, but there are more symmetries that you could discuss even in deep learning. So the first symmetry will be the translation symmetry. So this will be defined by the action of just translating the parameter vector theta by some constant real number alpha. Where does this symmetry occur in deep learning? This symmetry actually occurs in the final layer of the neural network immediately preceding a softmax function. So as we can see, the softmax function is translationally invariant. So if we were to shift theta by some constant alpha, you can see that in the numerator, it would pull out from the numerator, and the sum, in the denominator, it would pull out and cancel. And thus the output of the softmax function won't have changed no matter what the value of alpha was, or theta for that matter. And so those parameters, theta, would have translation symmetry, and thus their gradient and Hessian would have a certain geometric property. In this case, the vector field generating the symmetry is just the all ones vector, and so the gradient would be orthogonal to all ones vector. The sum of the elements of the gradient would be 0. The sum would be 0. And for the Hessian, it's that the all ones vector would be in the kernel of the Hessian. To just try to visualize that, to build some intuition here, is let's just consider a really simple case where we have 2 parameters, theta 1 and theta 2, and we have this, in black, we have this kind of pictorial picture of a really simple network where you take some value and then you scale it multiply it by theta 1 and multiply it by theta 2, and then in green, that's where we're applying softmax to those 2 neurons. And if we were to look at the gradient vector field for theta 1 and theta 2, it doesn't really matter what the loss is, it would look something like this. And as you can see, the vector field is always orthogonal to the all ones vector. which is in this case would be the theta1 equals theta2 line. Great. A different symmetry would be defined is scale. The next symmetry we'll consider is scale symmetry. So scale symmetry is defined by the action when we just take our parameters and we scale them by some positive real number alpha. This symmetry occurs in all of the parameters immediately preceding batch normalization, or for that matter, any normalization layer. So for example, for batch normalization, if we scaled the parameters theta by alpha, you would see that the expectation scales by alpha and the variance would scale by alpha squared, but square root. And so alpha would pull out from the numerator and denominator and cancel its effect. In this setting, we would get a more interesting gradient property. Here, the vector field generating the symmetry is theta itself. And so this would imply that for parameters with scale symmetry, their gradient is always orthogonal to them to that point itself, to theta themselves. And then for the Hessian, we get that the Hessian theta product is actually equal to the negative gradient. So again, to build some visual intuition, we'll consider this really simple toy case. We have two neurons and that connect to one neuron, and then we apply batch normalization at that neuron. In that setting, we would see that the vector field for theta1 and theta2 has this kind of circular dynamics where you can see that at any point in theta1, theta2 space, the vector field, the vector is always, the gradient that is always orthogonal to that point itself. And the last symmetry that we'll consider in this work is what we call rescale symmetry. They're very similar to scale symmetry, but rather than just scaling one set of parameters by alpha, we'll scale a different set by alpha inverse. And where does this symmetry reside in modern neural networks? This resides in the parameters immediately preceding and immediately following any homogeneous nonlinearity, but in particular, let's consider a ReLU nonlinearity. In this case, in this example, you can see that if I scale theta1 by alpha, let's say, and theta2 by alpha inverse, well, the alpha would commute through the max function, and it would cancel with the alpha inverse, and thus the output of the ReLU would be unchanged. And this would lead to gradient properties quite similar to the scale properties, but in this case, we have two inner products, one for one set of parameters and one for the other set, and similarly for the Hessian. And to try to build some visual intuition for this, we consider this simple scalar network where we just two weight theta1 and theta2 in a row, with in blue is the ReLU nonlinearity, and the vector field associated or the gradient vector field associated with this would have these kind of hyperbolic paths on it. And again, these aren't the only symmetries you could consider. For example, the rescale symmetry, we've been thinking of alpha as always just a scalar value, but in the setting, for example, when you have linear networks, in that setting, alpha could be a k by k matrix, and you would have the same properties would hold, the same kind of analysis style would hold. It's just that now you wouldn't have you would have a matrix products instead of just inner products of vectors, but the same process would hold. Also, it's worth noting that we discussed one property of the gradient, but in fact, there's more properties of the gradient that are induced by symmetry. And additionally, there are more properties of the Hessian, again, induced by symmetry that you can find in the appendix to our work. And this is really actually a unification of a lot of the existing literature in deep learning that have identified this structure in the gradient and Hessian in deep learning models. And so in the work, we also discussed a lot of the previous works and how and what properties they were identifying. And it's really that the lens of symmetry is a way of just kind of unifying this in a really clear way. So rather, a lot of these works might be under the title of implicit regularization or something along those lines. And the idea here is that the analysis style of identifying a symmetry and then finding the gradient or the Hessian properties without ever having to evaluate the gradient or Hessian itself is just a much cleaner, easier way to understand these, rather than actually playing with the chain rule. We don't have to now worry about whether or not we do or don't consider biases. It just becomes a function of if you can or cannot identify a symmetry. Okay, so in part one, we discussed this general property, symmetry, and how that constrains the loss and gradient of geometry. But what we would like to understand is how does that interact with the learning rule to say something meaningful about the trajectories that the network takes during training. So we'll start by considering kind of the simplest model for stochastic gradient descent, the simplest model for first order training that we can think of, which is just gradient flow. And this is the ODE, d theta dt equals the negative gradient. It's you can think of it as the infinitesimally when you take eta in the limit to 0. Or a gradient descent is really a forward Euler discretization of this ODE. And so we're going to think about this learning process, and we're going to ask, how do these learning dynamics interact with the geometric properties introduced by symmetry we identified in part one? So let's consider these simple toy cases first to build some intuition. So consider that we're initialized on in parameter space, theta 1 and theta 2, by this blue dot. And we're just moving according to gradient flow. And we can see that in this case, the blue dot is constrained to the hyperplane given by its initialization. In this case, theta 1 and theta 2 have translation symmetry. And so we would say that the parameters with translation symmetry, their sum, the sum of those parameters, or the projection onto the all ones vector, is constant through training. It's a conserved quantity through training. For scale symmetry, we see that we're constrained to some sphere given by our initialization. And so parameters with scale symmetry, the squared norm of those parameters would be conserved through training. And this goes back to the earlier question. In fact, this is why we were looking at the squared norm for those parameters, because we actually knew that those filters they observed scale symmetry. And for rescale symmetry, we would be constrained to the hyperbola given by our initialization, in which case the axes of that hyperbola are conserved through training. Is there a question? Okay, great. And so this is a really interesting interaction between symmetry and conservation, and this is really just a version of Noether's theorem. In this case, every symmetry of a neural network has this corresponding conserved quantity through training under gradient flow. And in fact, we know what that conserved quantity is, and it's just the projection of theta onto the vector field generating the symmetry. And yeah, so this is a quite interesting connection where Noether's theorem was thinking about Lagrangian dynamics. Here we're thinking about gradient flow dynamics, but the idea is equivalent. If there's a symmetry, then we have these conserved quantities in the parameters. Okay, I think now Hidenori is going to take over.
Yeah, thanks, Daniel. So from here on, so far what we have learned is that each of these symmetries that we can find in network architecture creates some of the geometric structure in the loss function. And by combining the symmetry and a simple gradient flow learning rule, the theoretical prediction that's going to come out from the combination is that each of these parameter combination should stay constant through training, as you can see on the right. However, as we have shown earlier, the empirical plot of the parameter combination, in this case, the norm of the weights, aren't constant. And if you overlay that too, then it becomes clear that these two, theory and empirics, doesn't match. And then the question is why? The answer is because our learning model was too simple. There are many components that this gradient flow model is missing when you compare it against a realistic optimizer like SGE. And then the components can be the gradient flow doesn't account for weight decay, or it doesn't have momentum. There is no stochastic sampling of the batches of the data. And then it doesn't incorporate the finite learning rates because the gradient flow approximation was only accurate in the infinitesimal learning rate limit. And from here, we're gonna talk about how we can incorporate these missing components that the realistic optimizer has. And in part 3, we're gonna basically derive more accurate equation of motion that can describe the discrete updates of the optimizers in a continuous time differential equation. In part 4, we're going to come back to the main storyline and then again combine the symmetry and now improve modified gradient flow, the equation of motion, to solve for the parameter combination dynamics. So let's just first construct a more realistic differential equation motion for discrete optimizer updates. So the starting point again is a gradient flow, but the first component that's simply missing is a weight decay. In weight decay, you can think of it as either adding the quadratic regularization term, or you can just think of that term as a part of the main loss function. But here we're going to just separate to make it clearer, the separation. So we're going to simply have this minus lambda theta term, which is going to confront the L2 regularization or weight decay for the case of SGD. And on the right, we have a simple visualization in the case of quadratic loss. And then the blue curve is a gradient flow, which doesn't incorporate the weight decay, and red curve is with the effect of weight decay. And as you can see, the weight decay term is pulling the trajectory inwards to the center. So how about momentum? So momentum basically tunes this d theta dt. It's going to show up as a coefficient in front of it. And the effect of that is that momentum accelerates the learning dynamics, rescaling time, but leaves the trajectory intact. And as you can see on the right, if you add this momentum term, the blue again is a gradient flow without momentum, and with momentum on the red trajectory, you can see that it's going through the same trajectory, but the red trajectory is moving faster ahead of the blue trajectory. And for the stochasticity, we model the batch gradient G as a noisy version of the full batch gradient, so that there is some noise added to the original full batch gradient. And one thing to note here is that since these geometric properties of the loss function we identified is really based on the, as a result of the structure in the architecture, it doesn't have any of the data dependence to have that orthogonal gradient and generate a vector field property. So these orthogonal condition, for example, holds for any of these randomly sampled batch of data gradients. And among these components, one thing that we want to highlight here is the effect of discretization of final learning rates. So gradient descent moves in the direction of the steepest descent, but due to a finite learning rate, it fails to remain in the continuous steepest descent path. And on the right, you can see this animation where the original gradient flow trajectory was a circular motion. It's closed loop with blue trajectory. But if you discretize it, since the gradient is always orthogonal to the direction connecting the center and the position, with a discrete finite updates, the radius start to increase, and it's going to take a spiral motion. And this is known as one of the major difficulty in numerical analysis when you try to discretize equation of motion in physical system, which is continuous in time, and try to describe it in a discrete simulation. Then people face this problem. And now we are facing this reverse problem where we want to model the discrete SGD updates by continuous time equation, and then we have to account for these effects in a reverse way. So the question is, does there exist a continuous equation of learning that can accurately model the effect of a finite learning rate? And we take an inspiration from partial differential equation analysis called modified equation analysis, which is a method for modeling the discrepancy introduced by a discretization of a PDE with higher order spatial or temporal derivatives. And the first example is a version where we introduce higher order derivatives of the loss, effectively modifying the loss landscape itself. And then similar approach was in particular featured in deep learning with a work that came out in a similar time, which they are titled implicit gradient regularization. But this modified loss approach basically from at the level of the loss, it penalizes the large norm of the gradient. And the way we can incorporate that in this modified gradient flow, or sorry, modified loss, is that by adding this Hessian gradient product, which is proportional to the learning rate eta. So if you take eta to the zero limit, this term disappears, but with finite learning rate eta, then there is this minus Hessian gradient term. And the way it distorts the trajectory in the, again, simple quadratic loss example is that, again, blue is a trajectory taken by a gradient flow, and black dots are the trajectory taken by discrete updates. And as you can see, the modified loss trajectory, the red curve, more accurately goes through these trajectory taken by real discrete optimizers.
Sure.
Another way to incorporate these effect of discretization is by introducing higher order temporal derivatives to modify the flow, the directory, and then we call the approach modified flow. So here, instead of having this Hessian gradient product, we have again a term proportional to learning rate, where that term is now replaced with the second derivative of the theta. So it's kind of adding some acceleration term. And as you can see on the right again, with this example, the original gradient flow trajectory and then the trajectory taken by discrete update is so far different. However, the red trajectory, which can model these modified effects, again, much better describing what's happening in the discrete world by using continuous time description. So in part 4, we're going to basically combine the ordinary introduced symmetry geometric properties and then the updated, much better continuous description of the learning dynamics of the real world optimizers, and then try to solve for the dynamics of the identified previously conserved quantity. So the question here is, how do weight decay, momentum, stochastic gradients, and final learning rates all interact to break these previously conserved quantities? So the starting point is now different from gradient flow. Before, we had a gradient flow as a simple approximation of the learning dynamics, but now we consider a more realistic continuous model for SGD with both weight decay and modified loss. So the next step of the analysis is to project the learning dynamics onto the generated vector fields. And here, as an example, we consider a case of scale symmetry, where the transformation was multiplying parameters theta by alpha, and then the associated generated vector field of that transformation is theta. So by projecting the above equation of motion onto this theta vector field, then you get the equation below, where the bracket stands for the inner product. And then we can simplify some of these terms using the geometric constraints we introduced earlier by symmetry. So the first term, this product or inner product of the gradient and theta, cancels. And then the second term, Hessian gradient inner product with theta, now becomes negative gradient norm squared. After this simplification, we can now look at the ordinary differential equation for the theta squared. And if you look at this form of the equation, we can also start to make some physical analogy. In this case, the physical analogy is that this doesn't have the second order temporal derivative term. So it's an overdamped driven oscillator where the lambda, which comes from the L2 regularization or weight decay, acts as a spring, and then it's overdamped, so there is no second order term, but then there is a friction that's damping the system, and the length of the spring corresponds to the norm squared, and what's driving the dynamics is actually something that's coming from the data, which is a data gradient squared, and this effect is proportional to the learning rate. So if, again, in the limit of infinitely small learning rate, this effect disappears, but with finite learning rate, the data starts to drive the dynamics. So now we've just went through the lesson for the specific case of scale symmetry, but we can repeat similar calculation for the case of translation and rescale. And then these are the expression that we can get as a result of solving the simple overdamped harmonic oscillator equation with external drive from the data. And each of these expressions, when we evaluate it empirically, then we get these trajectory that are coming from this, again, above analytical expression. And we can compare what we have gone from the theory with experiment and can confirm that these two matches exactly. So one thing that's really nice about having the above expression is it's not just we can just fit the data with almost 100% accurate prediction visually, but it can also give us a lot of insights about what's driving the dynamics of each of these parameter combination for the case of each of the specific symmetries. So for translation symmetry, theta inner product with 1, which is basically just a sum of these translationary symmetric parameter sets, decays exponentially to 0 at a rate proportional to the weight decay. And in this case, dynamics is independent of learning rate and data due to the lack of coverage in the gradient field. And what's nice about it is that if your friend train a network and then give you some training trajectory, then you can just look at, for example, say last layers, softmax function, find translationary symmetric parameter sets, and then you can just back infer what were the parameter, hyperparameter combination that your friend have used. So this is really clean dynamics that only depends on just a couple of hyperparameters that you can always backtrack. For the scale symmetry, we can predict again the dynamics of the norm, and then the norm is the sum of an exponentially decaying memory of the norm at initialization, which is a first term, and second term is basically exponentially weighted integral of gradient norms accumulated through training. And this norm, for the case of batch norm, may be important for someone, for example, thinking about the effective learning rate for the case of batch norm, because there are many literature recently connecting this norm with inverse of the effective learning rate, which might be controlling the training dynamics. So that's how you might care about the quantity. For the rescale symmetry, the expression is similar to the batch norm case, but the rescale and then the rescale dynamics do depend on the data through the gradient norms. But the one big difference is that unlike scale symmetry, which was just a norm, rescale symmetry is taking difference with two norms. So there is no guarantee that the integral term is always positive. And just visual inspection, we can see that the trajectory looks much more wigglier. And for each of these plots, we have 3 panels with different learning rates. And then we can see that as you increase the learning rate, the dynamic starts from something, for example, for the case of batch norm, the dynamics was basically just keep increasing the norm, but the final state of any of the dynamics is that as you make the weight decay stronger, then finally you're gonna start seeing these exponential decay kind of plot. So finally, let's also consider about the effect of momentum, because in the previous panels, we didn't consider momentum. So the continuous model for SGD with weight decay, momentum, and modified flow. So here we are adding higher order temporal, second order temporal derivative term, which is a first term. And as you can see, by making the learning rate finite and then increasing the momentum, this second order term starts to play bigger and bigger role. And we can go through the same setup procedure where we project the above equation of motion to the parameters theta that is a generated vector field of the dynamics. And we can get, again, the differential equation describing the motion of the parameter norm squared. And the equation above is now can be mapped to the underdamped instead of overdamped like last time driven oscillator. So here we again have these spring constant proportional to the weight decay. The weight norm acts like a length of the spring, and then we have driving force coming from the data, but now we also have this notion of mass because it's underdamped, and again the mass is proportional to the learning rate, and then it increases with as you increase beta. And this equation basically is suggesting something important, some qualitative feature that we might be able to see oscillating harmonic oscillator in deep network. And we have actually found them by inspecting different parameter regimes so that the dynamics change from the overdamped to underdamped case as you go to the right. And as you can see, with a carefully chosen hyperparameter beta equal 0.99, we can see this nice oscillation effect, which is like decaying oscillation at the last softmax layers translationary symmetric parameter sets. And if you could look at our paper in the appendix, we can also see similar oscillation. It's not just simply decaying for the case of other symmetries like scale symmetry, rescale symmetry, because the data start to play a role, but it's interesting that we start to see find these harmonic oscillators in VGG16 trained on Tiny ImageNet with SGD with momentum, which is what people use. So we're going to start concluding, and then let me first show you some conceptual overview, and in particular, why we titled our paper Neuromechanics this time. And in this work, we wanted to make some analogy between classical mechanics and physics, which describe how a particle moves in physical space, and the problem of learning dynamics in that analogy can be thought of as a model starting from initialization and then moving in parameter space as the training goes, kicked by data, driven by all these optimizers. And one of the starting point or foundation of the classical mechanics is a continuous time equation of motion that we learn as a Newton's law. And the corresponding object in the case of deep learning is that we have equation of learning, which we derived as a continuous time description of the real world optimizers like SGD or SGD with momentum. And after a one analysis, we have found that it's a damped oscillator driven by loss gradients. Another really important concept in mechanics is symmetries. And in particular, in physics, we learned that symmetries in Lagrangian leads to these conserved quantity like energy, momentum, and angular momentum for each of them, like translation space and rotation of the space. And then these kind of symmetry also, first of all, we can find in almost any of the parameters that's in the modern state-of-the-art deep learning models. And we have found in particular, this set of translation, scale, and rescale can describe almost any of the nonlinear function or even these like architectural building blocks like patchstone we can find in a modern setting. And then by combining these equations of motion and symmetries, we have conservation laws, as I've already went through, like energy, momentum, angular momentum are connected to the three symmetry above. And the same was true for the dynamics under gradient flow, which was a simpler one, but with more sophisticated modern optimizers, we have broken conservation laws, which can describe the dynamics of parameter combinations really accurately instead of them being constant. So conclusion and future work. So again, our work have found or developed two main hammers. The first one was symmetry. It's a unifying theoretical framework explaining how a network's architecture leads to geometric properties in gradients and Hessian. And we have derived the list of 15 formula that were partly known, but we unified and generalized them so that people could use. And in our case, we have combined these geometric properties with the modified gradient flow, which is a realistic continuous equation of modeling the SGD with weight decay, momentum, stochasticity, and discretization. And then the question is, now we have these two hammers, we combine them to derive all the nice analytically solvable dynamics. And then how can we connect these theoretical insights to practical application, or in other words, where are the nails? So this work actually, even though it's a theoretical work, it has originated historically from our previous collaboration working on neural network pruning, where the question was, we have to quantify how important each of the parameters in the network so that you can remove unimportant ones and then only keep important ones. And there, the pruning score, for example, that people use were typically the product of gradients and theta. And that's because it's a first order Taylor expansion of the loss. And then these product of gradient and theta is something that we also encountered as a part of the structure of the loss landscape induced by symmetry. And we have used some of the insight to construct an algorithm. And also, one of the most simplest and powerful pruning metric in the field is the magnitude pruning, where you just look at the magnitude of the weights after training and then just keep only the largest magnitude weights. And then that works really well. And the object that we have predicted, for example, for the case of batch normalization, we have norm for the parameters, and then we have analytical expression of how these magnitude for the set of parameters evolve during training, which can be useful for future exploration of the pruning algorithms. And another interesting example, which has similar question in the field, is a continual learning. Just like we asked how important each of the parameters in neural network pruning context, people also care about the quantification of the importance of each of the parameter, because their objectives is that after a network learning task 1, you don't want to forget the parameter, how it was learned in the task 1 when you move to the next task, task 2, and then they quantify the importance of the synapses for the task 1. If it's important, you don't want to move it too much when you learn a new task, etc. So with a similar logic with the pruning, there are some insights that people in recent work have used, which is insight originating from these loss landscape structure induced by symmetry. And another line of research that people actually have been kind of already doing a lot of exploration is scale symmetry with batch norm. There are really rich literature in this space. And in particular, one connection we want to highlight is that these norms of the parameter sets coming into the batch norm, which we now have analytical expression for, is something is that what the quantities associated with the inverse of the effective learning rate of the batch norm training. And by having analytical expression, we hope that it's going to help us better understand these auto learning rate tuning phenomena of the batch normalization. And again, these are just 3 specific examples, but we hope that our general theoretical framework can be applicable in many more places, and then hope you're going to find one. So in terms of the developments of the theoretical framework, so where we are now and where next. So our work basically sits at the intersection of the symmetry that are induced by architecture of the model, and we also incorporated the learning dynamics by constructing modified gradient flow, describing the learning growth. So it really sits at the intersection of the model and learning growth. However, the ideal deep learning theory should also consider another important component, which is a task or the data, which we are missing in our theory right now. In our future direction in terms of the developing the theory will be to push our theory upwards so that we can start talking about task, generalization, convergence, all those interesting theoretical mysteries that people care about in deep learning theory. And yeah, this is the end of our talk, and thank you so much for listening.
Thank you very
We're gonna
much
take questions. Yeah.
for the talk. Yeah, if there are any questions, please do ask.
Can I ask a question?
Yep.
So you have replaced the problem of finding the derivative to finding the symmetries. Is there a way that you, like a systematic way to identify these 1,000 symmetries?
Well, so in some ways it's relatively easy, just because when we add, let's say, some sort of block to the forward pass, like a batch normalization layer, we can just look at the form of that function and say, does that function possess that symmetry, or like the softmax layer? And it's not like we have to look at, and then because that batch normalization layer is applied after every convolutional transformation, and we look at how many neurons that is the output of that convolution, then we would say, oh, look, each of those neurons will have that symmetry. So I mean, it really just comes down to looking at all the building blocks of an architecture and asking, do those building blocks contain that symmetry? It's not like we have to look at each of the neurons individually. We just say, does the building block have the symmetry? And oh, the building block is applied to these couple thousand neurons, so those couple thousand neurons the parameters immediately preceding will all have that symmetry.
And is there also a way to detect the symmetries that are connected to a more intricate combination of this structure? Because it's quite non-linear, so you can have those maybe.
So like you're saying, detecting symmetries from just the dynamics, or like maybe like more complicated relationships between parameters at different layers?
Yeah, the latter, yes.
Yeah, so I mean, take for example the rescale symmetry. In the rescale symmetry, you had this relationship between consecutive parameters, right? Before and after a Ray loop, for example. And so that gradient property, you could start to, sorry, I'm just trying to find the spot here, right? That gradient property, you could start to say, well, if the parameters at layer 1 are related to the parameters at layer 2 in this way, and layer 2 is related to layer 3, in which case layer 3 and layer 1 were also related. But it's not introducing new symmetries. It's just really a different, it's just an artifact of the symmetries that already exist there. So I think it is important to note, for the symmetries we discussed, translation, scale, rescale, only rescale is acting on parameters from different layers. And that does create an interaction between layers, but that interaction doesn't introduce new symmetries. It's just really an artifact of that interaction between layers.
Okay. Because it occurred to me that since you made the analogy with Noether's theorem, which you can invert in some cases. So sometimes if you know of some conserved quantity, you could find quite exotic symmetries perhaps. So I thought maybe you use that as well, but maybe not.
Yeah, we didn't actually go that route, but no, that would be true. Like if for example, let's say under gradient flow, you observe that these norms were conserved, then if you can express that norm or that conserved quantity that you're discussing as an inner, I'm just trying to get to that, animations are slow, as this inner product between theta and some vector field, then that vector field would generate a symmetry. So you could conceivably invert this process, but I don't know if that would be a actually robust way of identifying symmetries, more robust than actually just looking at the computational graph that you are using in your network.
All right. Okay.
I had a question. Thanks for the very nice talk. About this translation symmetry, for example. So actually I had two, but the first is about these conversation laws. So you had several of them, I think tens or so, but then like the parameter space is actually much bigger, right? So you can't predict that these weights are walking in a certain subspace, but not exactly where, I guess, because you have only a few constraints. Or is it correct what I'm understanding?
Yeah, that's completely correct. So I mean, it's not unlike saying, oh, look, we're in R3 and we have 3 conservation laws, therefore we now can actually understand the entire trajectory based on the conservation laws. In this case, we have millions of parameters, but we have thousands of symmetries at a very different scale. So really, we don't see this as a way of trying to say, like, we don't see this as saying, like, now we can go back to that original picture and understand each individual element of the parameters and how they move. We see this really as just trying to uncover some general properties of the deep learning system. And I think that those properties do play roles. Ideally, we have shown they can play helpful roles in, for example, pruning or interpretability, understanding just norms of filters, but it's not like this gives the full picture at all. And so, there's, I think, as Hidenori discussed, there's a lot left to be understood. I don't think we expect, though, that analogy of like finding millions of symmetries and therefore the dynamics are exact. We don't expect that to be the case in this setting. We think that this is kind of a different analysis, and that we're not really sure what the next steps might provide, but we don't expect this to be like we're going to be able to now predict each of those wiggly lines I showed in the very beginning exactly. We don't expect that.
Mm-hmm. Yeah, then actually, I think the only exception that we have is a case of like linear network where the transformation is a K by K matrix, and then these symmetries, there are just so many symmetries that linear network essentially just going to restrict you so much that it cannot really express more than just what single matrix can do. So, I think it's kind of reasonably these networks that we use are more expressing that and that has more freedom left. Yeah.
In the case of Noether's theorem, it only applies to continuous symmetries. Obviously, there are many interesting non-continuous symmetries for neural networks. So I was hoping you could say something about to what extent the comparison to Noether's theorem is an analogy, or to what extent you think that a similar phenomenon might be at play, where there might be interesting symmetries that we can't get at because they're non-continuous.
Yeah, I might have glanced over that word, but in our definition, but we are only considering differentiable symmetries. And so we're not considering, for example, like permutation symmetries of where you can permute the order of the neurons in any hidden layer and change the.
Yeah, that's the main one I had in mind.
Yeah, and so it is a direct analogy. We're only considering symmetries that are continuous and differentiable. And that's why we're not, like, permutation symmetry would not be applicable in this analysis.
No, I understand. I was wondering if you had I understand that wasn't covered in what you did. I was wondering if you had a conjecture or hypothesis about whether similar work can be done with discrete symmetry. Finite discrete symmetries.
I'm not sure. I think that one of the lessons learned through this work for myself is that when considering really complex systems, such as a deep learning system, trying to find simpler ways of analysis rather than is a great strategy. Rather than getting lost in the weeds of chain rule, thinking about like, how can I simplify the problem? And if I look at maybe there's a simpler lens through which to look at the problem. And I think so. I don't know. This route, no, but potentially permutation symmetry would provide some way of simplifying analysis, in which case, in some sense, like the lesson would be the same, but it's not in this analysis.
Yeah. Okay. One thing that some of the research I'm doing right now is focused on is the role of the neural network architecture itself. And one thing I was really interested about when I was reading through this paper was kind of thinking about, graphs have automorphism groups and how some of these ideas might be applicable when talking about like the automorphism groups of graphs.
So I'm not sure I know much about that, but I think what that just reminded me of is something that we didn't talk about here is in deep learning, there's, a lot of work that talks about symmetry in the data set and how the network would reflect that symmetry in the data set. In particular, like for example, certain forms of permutation symmetries, like for why a convolutional block would be, like why a convolution makes sense when talking about images. And it sounds like, are you talking about like neural network graphs have a certain type of symmetry, and therefore you might want your architecture to reflect that. So I think that is a route that where you could imagine these discrete symmetries playing a role is how they interact with the data set. I don't know if that answers your question or not, but maybe.
Can I ask a question? So I don't know if this makes sense, but it's sort of an obvious thing to ask, which is all your symmetries are global. Now, of course, Inertia itself looked at local symmetries where we would have, for example, a translation in theta that depends on theta. So have you thought about something like that?
We didn't, and I think that generalizing these ideas, like one of the earlier questions we were asked in a different talk was like, okay, you're only looking at when alpha is a scalar. Like, well, what about more complex translations, for example, translating by some arbitrary vector or translating the data itself, or something along these lines? I think it's a good question, and I don't. We looked at these simply because these were the symmetries we could identify in the convolutional neural networks we were looking at. We didn't think more broadly about maybe like what are like for example, there's many other blocks of deep learning architectures like transformers or attention and stuff along these lines, different recurrent neural networks. Where would symmetries reside in these other architectures? Or maybe you could take a route like what you're saying is maybe there's a property you would like, and then can we build a block that contains that kind of symmetry if you had some reason to believe that this is a property you would want in your system? But we didn't really more broadly consider we really didn't consider anything else other than the ones we discussed, just because those were the ones that were the lowest hanging fruit, per se. Yeah.
I mean, it may not help you at all because local symmetries don't have conserved quantities. So it may not help. It's just a physics analogy that's very strong, that's all. But okay, thanks.
Yeah, thank you for that stuff.
A quick question about the underdamped systems. It seems to imply that if you care about minimizing the or getting to the conserved value the fastest, you'd want to critically damp all of the things that you could critically damp, and this might translate to better performance during training. Did you experiment with seeing what happens when you set to the model performance during training if you set the beta, the momentum parameter, to what's implied to be critically damped according to your formula?
So at first when we were, this is a great question. At first when we were kind of noticing this relationship between the overdamped and underdamped setting based on the hyperparameters optimization, we were thinking, oh yeah, maybe that's it. Maybe like the hyperparameters that are commonly chosen are really chosen in such a way because it gets you as close to that critically damped setting as possible. So we started experimenting, looking at like performance, showing like like some plot where we would try to measure performance and relate it to whether you're overdamped or critically damped. And we really found that like the underdamped settings were incredibly unstable. Like it was very confirmative to realize that we could push this network into an underdamped regime and observe oscillation, but it would never be a model. You would never be in that setting. And even the critically damped ones that we were looking at didn't seem to be performing that well. Most of the common hyperparameter choices were always in this overdamped regime. But I think it could be a good question, like for example, like given that the last linear layer, the last classifier layer is, exactly the dynamics of each of the column sums, even at the beginning of training, it does make sense, like maybe you might want to just enforce those as constraints from the get-go, and maybe that would be lead to stabler or faster dynamics. I'm not sure. But yeah, that intuition that you're saying is like we had a similar intuition, but it didn't seem like the pattern was super obvious, but maybe the pattern is there.
It also looks like this implies that there's a different critical damping for each parameter block, though like I think standard operating procedure for SGD plus momentum is to use the same momentum everywhere. Did you try, or your experiments, were they like separate momentums for each parameter block, or like according to its value, or like global values?
No, just standard out of the box. So this, a single global momentum parameter, single global lambda, single global learning rate. Yeah.
Thanks.
So I was also wondering, in the super cool picture where you mesh the theory and experiments, at time equals to 0, did you choose specific parameter configurations, or it's typical initialization?
Yeah, just that I some Gaussian, like Glorot initialization, something standard like this. I can't I don't know exactly right off the bat what it was, but it's just typical initialization.
Could I ask a question? Actually, I have several, but I'll just start with one. In the very last slide, when you talked about pruning, can you say a bit more about how you, what you have in mind? So are you thinking of using these equations for doing pruning at initialization or like early on in training? Because it looks like you need some information about the gradients at different times, input into the framework to be able to predict kind of the evolution of the weights. Is the hope that maybe you'd be able to do that early on in training with just?
So there are like two kinds of things. The first thing that we have used in this previous particular work was that we even didn't use all the learning dynamics part. We simply used the fact that if you have a ReLU activation, then the gradient and theta inner product is something that people use as the pruning score. And then basically the intuition was that these pruning score that people use have these like a layer-wise conservation law, in a sense that if you add up all the pruning neuron synapse importance score per layer, then that's equal. So what the cost was that if you have like last fully connected layer that has tons of parameters, and then earlier layer that has much less parameter, then since their sum of the importance score is always have to be some fixed constant, that they were basically just, their average was inversely scaled with the layer size. And then when people did the pruning, global pruning, these algorithms were pruning too much from the last layer simply because last layer had too much parameters. And then we introduced an algorithm that kind of solves the issue by iteratively evaluating this, importance score so that things are always at the conservation. So that was more specific thing that we had in mind. But then, yeah, this paper also has like a small section about trying to better understand the lottery ticket hypothesis. And at that time, one of the, for example, hypothesis was that at least under gradient flow, these conservation laws says that the magnitude of the synaptic connections coming into a neuron and coming out from the ReLU, again, neuron should start to be equal with weight decay. And then we thought that, okay, so these magnitude might also have these conservation law that we have talked before. And then again, that might explain why the lottery ticket algorithm that does iteratively magnitude pruning had to iterate again and again based on the insight from conservation law. These are just naive initial thinking, but extending these lines of thinking with the updated version of our theory might help, is our hope. Yeah.
Thank you. Other questions? Otherwise, I might ask one other question. So you mentioned a body of work on implicit regularization early on, and it's really nice to see that you like unified it or some part of that with this work, which is really nice. I'm curious what your take on now after having done this is on some of those earlier works, because like, would you say that then many of them are just studying the implicit regularization due to symmetry, or they somehow work in some information about the data as well to say something about generalization?
Yeah, so one specific comment is that like, for example, there are some particular work where they coupled again with all the symmetry constraints and then the simple gradient flow dynamics, and then said, for example, these again magnitude of the weights coming into a neuron and coming out of the neuron have to be equal. So it's a constraint. But then one simple takeaway from our work is that that is just not the case if you have finite learning rate, because these conservation laws that they use as a logic for implicit regularization is simply broken after you move away from the gradient flow. So there is no such regularization in a strict sense that we can find in a real network is one of our conclusion, maybe except for the translationary invariant case. And yeah, Daniel might have more to say, but yeah, that's my
I think like my take is that implicit regularization is a pretty blanket term, and actually demonstrating that there's a connect, and generally I think it was used as saying, look, it's not very intuitive, right? We initialize our networks randomly. All the weights are initialized randomly. Our data sets are super complex. And so to then show that, in fact, actually there's structure in the gradients, at least for me, it was not a very intuitive thing. I would have kind of assumed at any point in training and any point in parameter space, I would have assumed actually no, that how could you, like these gradients would be highly random or highly dependent on the data and parameters, which were random. And so that this is kind of confusing. And so in some sense, I think when you find structure in something you expect to be random, you're saying, look, that means that's a form of implicit, that's somehow regularizing the system. It's making it simpler, which is true. But then connecting that to actually generalization is a difficult task. And so I think there's some implicit regularization works, in particular the ones that are coming to my mind right off the top are works that are kind of using the kind of the energetic entropic view of neural network training and seeing that as the entropic, this idea of that the solution is trying to also maximize entropy of this stationary solution. That to me is like very different than what this is. But so I don't see this as like a unification of all implicit regularization. I simply see it as the unification of the implicit regularization works that were focused on structures in the gradient. And a lot of this was kind of individual snippets looking at structures given by homogeneous nonlinearities or the structure introduced by batch normalization. But I think seeing that as like, oh, it's just if there's a symmetry, then you have the structure. That's where we're unifying. And then actually by connecting that to what regularization is meant to do, which is improve generalization, our work does not do that. That's why we're really trying to figure out this where next component. And I think, so I hope that kind of gives some lens, some contextualization to when I was saying like a general or unifying some implicit regularization works.
Thank you. And actually on this Venn diagram, do you even think that like there will be an intersection here? Like there's an intersection, I think, for like between learning rule and task. But do you wonder if perhaps symmetry, the things that are due to symmetry are actually the things that don't so much have to do with learning? They're kind of like orthogonal in some sense. And you, I'm curious if that.
Yeah. So that's a good point. And then, but like I think one important fact that we still find interesting is that like all the symmetry that we talked about is just a symmetry of the loss function. But if you think about the, like Lagrangian governing the dynamics or, the actual learning rule, these optimizer actually doesn't have a symmetry or similarity in the sense that even for the batch norm, if you have one initialization for the parameters with batch norm, and then if you scale some of these parameters, in some distinct way, and then create another initialization with, different initialization norm, then even though the network function doesn't change due to the scaling, the learning dynamics does get affected. And then that's kind of, it is a specific way of affecting the learning dynamics, but it's still, I think it's important that symmetry basically implies that it doesn't change the function. It doesn't basically just matter. The loss doesn't change. So it doesn't matter in that sense, but the learning dynamics or the updating rule does get affected by symmetry. And then that's, for example, this like effective, auto learning rate tuning effect, for example, is something that we are hoping to have like a clean analysis while still connecting to the, some of the mystery about the neural network training dynamics, which again is not, equivalent or similar or symmetric. Yeah.
Cool, thank you. Any other questions? If not, I think we should end here.